Good morning, everyone. Welcome to this last lecture of this course. Today, we're going to learn about representations of integers. In everyday life, we use the decimal notation to express the integer. For example, if we take an integer 975, then in a simple English, we read it as 975, where the 900 part you represent by 9 times 10 to the power 2, 70 as 7 times 10, and 5 is a plus of 5. Okay, so with respect to the base b equal to 10, we can use the following decimal expansion to represent the integer 975. In particular, computers usually use binary notation with the base equal to 2 when carrying out arithmetic, and octal with the base 8 and hexadecimal with the base 16 when expressing a characters such as letter or digits. In principle, we can use any integer greater than 1 as the base when expressing a given integer, and this is stated in the following theorem. So let b be an integer greater than 1, then if n is a positive integer, then n can be expressed uniquely as n as the linear combination of power of bi's, where ai's are my coefficient. So n can be written as ak times b to the power k plus ak minus 1 times b to the power k minus 1, and all the way up to a1 times b plus a of 0, where k is a non-negative integer and the coefficient a of i's, they are satisfying a special condition that they are non-negative and they are less than your base b value. The highest coefficient a of k is not going to be equal to 0 here. For our above problem, we can say that if we use the decimal notation, then 975 is going to be equal to 975 with the base 10, where the coefficient a of 0 is 5, a of 1 is 7, and a of 2 is going to be equal to 9. And the base value here, b, is going to be equal to 10. That's the reason you are able to express 975 as 9 times 10 to the power 2 plus 7 times 10 to the power 1 and plus 5. The representation of n as given in this theorem, where n is written in the linear combination of the power of b of i's by using the coefficient a of i's, where a of i's has a non-negative integer and has a value less than the base value. They are called as the base b expansion of n. And in short, you can collect all those coefficients and put them inside a bracket, and if you use a base b here, this is the short form representation of the base b expansion of an integer n. For example, with respect to the base 2, if I have the base 2 expansion of n, which is 1 1 1 with the base 2, it has a meaning that you can expand it, that the first coefficient a0 is 1, so is 1 times 1, plus the second coefficient is also 1, so is 1 times 2 to the power 1, plus the third coefficient is also 1, so 1 times 2 to the power 2, so that's going to be equal to 7. Similarly, if you have a 2 4 5 with the base 8, then a0 will have the value 5, a1 will have the value 4, and a2 will have a value 2. So you can write them as a base 8 expansion of an integer n, which is going to be equal to 5 times 1 plus 4 times a to the power 1 plus 2 times a to the power 2. And if you simplify, that's going to be equal to 165. In this table, we have 4 different representations of an integer from 0 to 15. The first column represents the decimal representation of an integer from 0 to 15, and with respect to the base 10, the decimal representation of the integer is going to remain same. So starting from 0 1 2 3 4 and all the way up to 15. So if we take any integer value from 0 to 15 here, for example, if we take n is equal to 9, so 9 can be represented as 9 with the base 10. Okay, which is going to remain itself. With respect to the second column, it represents the binary representation with respect to the base b equal to 2, and the digits which is allowed in this base 2 expansion of an integer, they can have a value greater than or equal to 0 and less than the base value. So that means only the value of 0 and 1 is allowed here. So with respect to this 9 integer, I will have a binary representation which is 1 0 0 1. With the base 2 you can expand by taking the power of 2 as 2 to the power 0 here, 2 to the power 1 here, 2 to the power 2 here, 2 to the power 3 here, and multiplying it with respect to those coefficient. So you can write is 1 times 2 to the power 3 plus 0 times 2 to the power 2 plus 0 times 2 to the power 1 plus 1 times 2 to the power 0, which is basically equal to 8 plus 0 plus 0 plus 1 is going to be equal to 9. So this way you can expand the binary expansion and get the integer value. The third column represents the octal representation of integers from 0 to 15 with respect to the base 8. So for an integer 9, in octal representation 9 is represented as 1 and 1 with the base 8, which you can write as 1 times 8 to the power 1 plus 1 times 8 to the power 0. Okay, so it has only two coefficients, 1 and 1, and if you write in a expansion form, that's going to be equal to your 8 plus 1, and that's going to be equal to your integer 9. In case of hexadecimal, we allowed the digit from 0 to 9 to represent an integer, and then after that we use a character. The A is a representation of 10, B is a representation for 11, C is a representation for 12, D is a representation for 13, E is a representation for 14, and F is a representation for 15. So this is a special case when we allow the character to represent the integers, and that means D with the base 16 is going to be equal to 13. Okay, while if you have a case of 2D of 16, it has a meaning that is 2 times 16 to the power 1 plus 13 times 16 to the power 0, which is going to be equal to 32 plus 13. This is your 45 as an integer. So 45 as an integer you can represent in a hexadecimal system as 2D with the base 16. So if we have a base p expansion of an integer, then we can use our previous theorem and we can get that integer value. Now we're going to learn how to get the base p expansion of any integer. So in this example, we're going to look at how to obtain the binary and octal expansion of the given integer, which is 192 here. So on the left side, we represent the binary expansion of 192. On the right side, we'll represent the octal expansion of 192. So for an integer 192, we can use our division rule. So 192 with the base 2 can be written as 96 times 2 plus of 0. And if you take this quotient to the next level, then 96 can further be written as 48 times 2 plus 0 with a base equal to 2. And again, if you rewrite this quotient, then 48 can be written as 24 times of 2 plus of 0. And again, if you take this quotient, then 24 can be written as 12 times of 2 plus of 0. Keep doing the same thing, then the quotient 12 can be written as 6 times 2 plus of 0. Then the quotient 6 can be written as 3 times of 2 plus of 0. Then the quotient 3 can be written as 1 times 2 plus of 1. So 1 is the remainder here. And again, the quotient 1 can be written as 0 times of 2 plus of 1. And when your quotient becomes 0, then you stop there. So you are using the division rule every time with respect to the given base, which is 2 here. You are writing the given integer with some quotient time with respect to that base and plus some remainder term. And you are going to successively apply this division rule till the time you will get your quotient equal to 0. Once your quotient becomes 0, then you stop applying the division rule. And then you collect all those remainder from your last step to the first step and write them from left to right. So if you write it here, so the first is 1, which is the remainder here. Then another 1, which is the remainder here. Then 0, and 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 then 0. Then you have those many zeros. Okay, so you have to write from left to right in your expansion, and with respect to the remainder from bottom to top. So the binary expansion of 192 is 11000000 with 6 zeros with the base 2. Okay, so you can apply the division rule. You can write any given integer in the form of quotient times with respect to the base plus some remainder, and you have to apply your division rule successively till the time your quotient becomes 0. Once your quotient becomes 0, you stop there and you collect all the remainder from bottom to top and write them in your expansion from left to right. Okay, so the binary representation of 192 is 11000000. Similarly, now you can use this algorithm to get the octal expansion of 192. So 192 can be written as 24 times of 8 plus of 0. Okay, so the quotient is 24 here. And then this quotient 24 can be written as 3 times of 8 plus of 0. Now you have the quotient which is 3 here. And then this 3 can be written as 0 times of 8 plus of 3. So when your quotient becomes 0, you stop. You stop applying that division rule there. And the algorithm says that you collect all the remainder from the bottom to top and write them from left to right. Okay, so here you write them from left to right as 300. So 300 with the base 8 is going to be equal to 192. So this is the octal expansion of 192, which if you want you can verify that 192 can be written as 3 times 8 to the power 2 plus 0 times 8 to the power 1 and plus 0 times 8 to the power 0 here, so which is going to be equal to 192. So you can verify that. Let's take another example, and here you want the hexadecimal expansion of 692. So with respect to the hexadecimal representation, your base is going to be equal to 16. Your given integer n is going to be equal to 691. So in the first step, you apply your division algorithm with respect to the base 16. And can you represent the 691 in terms of some multiple of 16 plus some remainder term? We can get the quotient by applying our floor function, which is the value of n divided by b here. And in this case, if you take the floor value of 691 divided by 16, then you'll get the 43 here. Okay, so 691 can be written as 43 times of 16 plus 3 is the remainder, 43 is the quotient. Then you apply your algorithm, and next time you represent this quotient as a multiple of 16 plus some remainder, and you can represent 43 as 2 times of 16 plus of 11. Your quotient is 2, remainder is 11. 2 you can further represent in terms of a multiple of 16 plus some remainder, which you can write as 0 times of 16 plus of 2. And whenever your quotient becomes 0, you stop applying your division rule there. Okay, and then the rule says that you collect all those remainders from bottom to top and rewrite them in expansion from left to right. So in principle, we could have taken 691 with the base 10 is can be written as 2, 11 and 3, because these are the 3 remainder here, here and here, and with the base 16. But remember, in the case of hexadecimal system, we don't have 11 as a digit, but instead of that we have a character, and the representation of the 11 is going to be B, because you start with A as a 10 and B is going to be 11. So you can say the solution of this problem is going to be equal to 2 and the character B, and then 3 with the base 16. So this is the example to see how you can apply the division rule to get the hexadecimal expansion of any given integer. The next thing we're going to learn how to convert one expansion system into the another expansion system. So for example here, can you find the octal expansion of this binary expansion of an integer which is given in the form as 1 1 0 1 0 and 1 1 1 with the base 2. So the question is, can you find the octal expansion of this given binary expansion? Okay, can you find those digits here? Okay, so there's various way you can solve this problem. The one way you can convert this binary expansion to the decimal system, and then you can convert the decimal system into the octal system, and that could be a two-step procedure. Okay, the another way you can convert it directly by using the base value with respect to the binary expansion and the base value with respect to your octal expansion. So we know in terms of your octal expansion the base is going to be equal to 8. In terms of your binary the base is going to be equal to 2. But if you take the octal base 8, you can write as 2 to the power 3. Okay, that means if you combine 3 digits together in your binary expansion, then you can get the octal expansion from there. Okay, so you start from right side and you move to the left side and you start making a pair of 3 digits. So the first I can make a pair of these 3 digits, then I can make a pair of these 3 digits, and then I left with only 2 digits. So what I can do, I can put a 0 here and I can make a group of these 3 digits here. So I will have these 3 groups here. Okay, remember, if you have enough number of digits to make the group of 3 digits together, you take that. If you don't have enough number of digits, so you put the zeros on the left side. Okay, you are supposed to put the zeros only on the left side, not on the right side. So here we have 3 groups. So the first group is 0 1 1, another group is 0 1 0, and the third group is 1 1 and 1. Now if you take this first group in a binary expansion form of 0 1 1 with the base 2, so this you can write as 0 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0, which is going to be equal to 0 plus 2 plus 1 is going to be equal to 3. Similarly, you can write this binary expansion of 0 1 0 of 2, and that's going to be equal to 0 times 2 to the power 2 plus 1 times 2 to the power 1 plus 0 times 2 to the power 0, which is going to be equal to 2 here. And 1 1 1 with the base 2, so you can say, is going to be equal to 1 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0, which is going to be equal to 4 plus 2 plus 1 is going to be equal to 7. And since these groups are appearing on this binary expansion from left to right, and 0 1 1 is going to be a representation of 3, 0 1 0 is going to be a representation of 2, 1 1 1 is going to be representation of 7. So you put them from left to right. Okay, so you put them from left to right in your octal representation expansion. So here the first is going to be your 3, then it's going to be 2, and it's going to be 7. So the octal expansion of 1 1 0 1 0 1 1 1 with the base 2 is going to be equal to 3 2 7 with the base 8. You can use the same logic to get the binary expansion from your hexadecimal expansion. So in your binary expansion, your base is going to be equal to 2, For your hexadecimal, your base is going to be equal to 16. So 16 you can write as 2 to the power 4. This gives an indication that here you need to make a group of 4 digits together to relate your binary expansion with your hexadecimal expansion. With respect to this given problem of A and 8 with the base 16, the leftmost digit is A here, which is equivalent to 10, and 10 you can represent in a binary expansion form as 1010 with the base 2. The rightmost digit here is 8 with the base 16 is going to be 8 in a decimal expansion, and 8 in a binary expansion you can represent as 1000, okay, with the base 2. Then you can use this binary expansion of A and 8 to get the binary expansion of A and 8 with base 16 is going to be equal to, the replacement for A is 1010 and the replacement for 8 is going to be 1000 with the base 2. So if you make a group of 4, you can convert a hexadecimal expansion to the binary expansion, and if you do the totally opposite, you can convert a hexadecimal expansion to a binary expansion. With respect to this base B expansion of integers, you can do 2 operations. The first is your addition. So you can add 2 base B expansion together. So in this problem you have to add A and B, which is given in a binary expansion form. So to add them, you write them as 1100, and the second integer B is given as 1, 1 and 1, and then you don't have a place here, so you put a space here. So your space could be that you have no entry here, you have no digit here, and then the first expansion will have 4 digits, the next expansion will have 3 digits, but they will have the same base. Once they have the same base, you can add them together, and the algorithm is going to work as you want to add them, you don't have the 4th digit in your second integer, so you start adding them from rightmost digit. So first you add 0 plus 1, so 0 plus 1 is going to be equal to 1. 1 you can write as 0 times of 2 plus of 1, so the remainder here is 1 and the quotient here is 0. So you're going to put the remainder here as 1 and you're going to take the quotient as a carry, okay. Then in the next step you're going to add this second column. So second column is 0 plus 1, which is further 1, and 1 you can represent as 0 times of 2 plus of 1. Again you have the quotient 0, remainder 1, so you put a 1 here and take the carry as a quotient 0. Now you need to add this 0 plus 1 plus 1, so 0 plus 1 plus 1, which is going to be equal to 2, and 2 you can represent as 1 times of 2 plus of 0. Now you have a quotient 1 and the remainder 0, so you put the remainder here 0, take the quotient in the next step as a carry, okay. And at the last step you don't have any digits at the 4th place with respect to the second integer. If you want, you can put a 0 there, otherwise you keep the as an empty place. So this time you have to add 1 plus 1, okay. So 1 plus 1 is 2, and 2 you can write as 1 times of 2 plus of 0. So again you write a 0 and then you take a carry as 1, and next time you just have a 1, so you put it here, okay. So the addition of A and B here is going to be a plus b is going to be equal to 1 0 0 1 1 with the base 2. Okay, so remember, by applying our division rule and taking the quotient as a carry and remainder you put in the addition of this problem, you can add two integers together. Let's take another problem, and this time want to add an integer a and b, where they are given in a octal expansion form. So a is your 2 2 and 2, b is your 7 7 and 7. Okay, and you want to add them. So first you're going to add the rightmost entry, which is 2 plus 7. 2 plus 7 is 9. 9 you can write with respect to the base 8 here as 1 times of 8 plus of 1. Okay, so the remainder is 1 here, the quotient is 1, so the remainder will go here and the quotient will become a carry. So the carry is going to move forward. So you have a carry of 1 in the next step. Next time you're going to add 1 plus 2 plus 7, which is going to be equal to 10. 10 you can write as 1 times of 8 plus of 2. So the remainder here is 2. You're going to put here. The quotient is 1. It's going to be a carry for the next step. So it's going to be next step again you're adding 1 plus 2 plus 7, which is going to be equal to 10. 10 you can write as 1 times of 8 plus of 2. So the quotient is 1 here, the remainder is 2 here, so 2 will go here and the quotient will become a carry for the next step. And in next step we are just adding a 1 here. So the addition of 2 2 and 2 with the base 8 with 7 7 7 with the base 8 is going to be equal to 1 2 2 and 1 with the base 8. In our previous example we learned how to find the sum of two binary expansion. Let's look at another example, and this time we want the sum and product of the octal expansions, okay, with respect to the base 8. So the a here is 763 with the base 8 and b here is 147 with the base 8, and you want to add these two octal expansion of a plus b. That means you are interested in finding the sum of 763 with the base 8 and plus 147 with the base 8. Okay, so the way we are going to add these two, so we take 763 and add with 147 with respect to the base b equal to 8. So the rightmost entry here is 3 and 7. So first we're going to add 3 plus 7, which is going to be equal to 10. 10 you can write as 1 times of 8 plus of 2. So the quotient here is 1 and the remainder here is 2. So you're going to write the remainder 2 here and you're going to take the 1 as a carry for the next step. And next time we are adding 1 plus 6 plus 4, which is going to be equal to 11. 11 you can write as 1 times of 8 plus of 3. So this time I have a remainder 3 and my quotient is 1, so my carry for the next step is going to be 1. And then I'm adding 1 plus 7 plus 1 in the next step, which is going to be equal to 9. 9 can be written as 1 times of 8 plus of 1. So my quotient and remainder in this case, they both are 1 and 1. So I'm going to put a 1 here, and in the next step I'm going to take 1 as a carry. And if I add, then in the last step I'm going to put a 1 because I'm only adding the 1 here. Okay, so the addition of 763 with the base 8 with the 147 with the base 8 is going to be equal to 1132 with the base 8. Let's see how you're going to do the product of 763 with the base 8 and doing a product with 147 with the base 8. What will be that number equal to with the base 8? Okay, so to answer this question we're going to do the product in a useful way. So 763 is going to be my first integer with the base 8 and 147 is going to be my second integer, and I'm going to do the product of these two. expansion. So first I need to compute this first row, and first row is the 763 with the base 8. I'm going to multiply with 7. Okay, and then I need to compute 763 with the base 8, going to multiply with 4. Okay, so 763 is going to multiply with the last digit here, which is going to be equal to 1. So it's going to be equal to 763 times of 1. And once I have these values with respect to these three products, then I can take them as the first row, second row, and third row after doing the shifting towards the left side, and then I can add my three rows together to get the product of these two expansion. Okay, so to fill up the first row, we need the value of 763 with the base 8 times of 7. Okay, which if you multiply, then 7 multiplied with 3 is 21. 21 you can write as 2 times of 8 plus of 5. So remainder is 5, quotient is 2. So you can say when 7 multiplied with 3, you get 5, and your carry here is going to be equal to 2. Okay. The next time when you multiply 7 with 6 is 42, and plus of 2 is going to be your carry. So 6 times of 7 plus of 2 is going to be equal to 44. 44 you can write as 5 times of 8 plus of 4. So the remainder is 4 here. The quotient is 5. So you put the remainder here 4. Now your carry will become 5. Then you multiplying 7 with 7. 7 times 7 is going to be equal to 49, and plus your carry 5 is going to be equal to 49 plus of 5, which is going to be equal to 54. 54 can be written as 6 times of 8 plus of 6. So my quotient is 6 here, and the remainder is 6. So in that case, I will put a 6 here, and my carries become 6, and which is going to be one more 6 here. So I can have a representation of my 763 with the base 8 multiple of 7 is going to be equal to 6, 6, 4, and 5 with the base 8. And similarly, I can find the product of 763 with the base 8 with 4 is going to be equal to 3, 7, 1, and 4 with the base 8. And the product of 763 with the base 8 with 1 is going to remain as 763 with the base 8. Okay, so once we have these three products, we can put them as the first row, second row, and third row in the product of this expansion. So the first row is 6, 6, 4, 5, and then you do the shifting towards the left side, and then you write the second row as 3, 7, 1, 4. So 4 will be here, 1 will be here, 7 will be here, 3 will be here, and then you do one more shifting. So you shift 2 places to the left, and then take 7, 6, 3. So 3 will be here, 6 will be here, and 7 will be here. And if you add them together, then again you can use your base 8 in this addition. So the first addition of the column, this rightmost column, is going to be 5, and 5 you can represent as 0 times of 8 plus of 5. So 5 is the remainder here, 0 is the quotient. So in this case I will put a 5 here, and my carry is going to be 0 here. Next time I'm adding 0 plus 4 plus 4, which is going to be equal to 0 plus 4 plus 4 is going to be equal to 8. 8 you can write as 1 times of 8 plus of 0. So the remainder is 0 and the quotient is 1. So remainder is 0 and the quotient is 1. So my carry will become a 1 here in this next step. Then I'm adding 1 plus 6 plus 1 plus 3, which is going to be equal to 11. 11 is going to be equal to 1 times of 8 plus of 3. So my remainder is 3, quotient is 1. So I'm going to take remainder here as 3. My carry for the next step is going to be 1 here. Then in the next step I'm adding 1 plus 6 plus 7 plus 6, okay, which is going to be equal to 20. 20 I can write as 2 times of 8 plus of 4. So my remainder is 4. My quotient is 2 here. So I will put a 4 here, and my carry for the next step is going to be 2 here. Then I'm adding 2 plus 3 plus 7 in the next step, which is going to be equal to 12. 12 I can write as 1 times of 8 plus of 4. So my quotient is 1 here, remainder is 4 here. So I will put a 4 here and I put a 1 here. So this way I can obtain the product of 763 with the base 8 with 147 with the base 8, and the product of these two expansion is going to be 14305 with the base 8. So in this lecture we learn how to use the different representation of integers with respect to the base 10, with respect to the base 2, base 8, base 16, which are the popular bases. We also learn how to convert from one base expansion to the another base expansion. We also learn how to do the operations such as addition and multiplication operations with respect to this expansion.